overview of the economical aspect related to the sea. So I will not go there. I'm a chemist, as I said. These are, and
Giuseppe. Sorry, I don't see the presentation. Can you try to?
The student can see the presentation, but they said you can see.
Yes.
Yes, yes.
Yes, but can you try to restart, because otherwise the recording is not going well.
So what
try one more time to. I don't know why I don't see.
Okay.
Sorry.
Sorry for the interruption, Prof. Goffredo. I'm present, even if a bit late.
Okay, thank you.
Thank you. Sorry.
Try to put a full screen. Okay, now we saw two slides now. The first one and the second one.
Okay, now you should see.
Yeah, now it's working. Okay, thank you. I also, Giuseppe, if you agree, I'm recording the presentation.
Yes, I find that you record a presentation, but I want to ask the student, don't put on the web this presentation. It's not to be free access. Okay, Stefano? Because there are some data that we didn't publish yet, so are sensitive data.
Okay.
Okay, so I was telling you that I'm a chemist, and I explained you all the story of my collaboration with Stefano Goffredo, and this is one of the ways I was involved in a marine resource and how to valorize marine resource. Now, as I told you this morning during the Steve Weiner lecture, I think it's very important to study the literature. And this is a concept that appears in Nature. Can you see the pointer?
Yes.
Okay. Nature is one of the most important journals for publishing a research article. And they clearly say, don't waste seafood waste. So it's clear that there is a treasure in seafood waste that has been so far not too much valorized. So turning cast-off shells into chemical will benefit economy and environment. Think this, every year about between 6 and 9 million tons of seafood waste are produced globally. So these numbers are really impressive. And the few lines that I wrote down here give you an idea where it comes out, these numbers. If you think tuna fish, you can recover about 75% of meat, and the other is waste. Now, if you move to mussels, which will be one of the topics of my study, the amount of meat that you recover is about 30%. What means this? That we have 70%, almost 70% of waste materials. And what is done with this waste material? The amount of this waste material which is recovered is very low. In developed countries, waste tails are often dumped in the landfill or in the sea, and this has a terrible environmental impact. Where in developed countries, they are disposed, but this can be costly. I'm writing here down that in Australia it can cost even up to 150 US dollars per tons. What molecules we have in waste seafood? What we recover from the waste seafood, and what we can valorize. And this is now the next slide. So we have in shells, we have 3 primary chemicals that can have industrial uses. The first one was already introduced this morning by Professor Steve Weiner, is calcium carbonate, and you will see where it is used. Then we have chitin, which is a polysaccharide, and proteins. So we can see the inorganic, organic, organic. if we are able to refine these components and give them a value, this will be $1 billion business in the bioeconomy. Now, let's start to discuss a bit about calcium carbonate. A few words about calcium carbonate, which is the first topic of my presentation. I think that every one of you knows calcium carbonate, but I think few of you are aware of how much is important calcium carbonate in our society. What I'm showing you here is a graph of the distribution of calcium carbonate along the continents. You can see that it's widely used almost everywhere. Not only, if we consider now the market of calcium carbonate, is growing up with the time, is expected to have a 6% CAGR increase, and by the year 2027, it is supposed to reach the value of $28 billion US. So for sure, there is a great interest in calcium carbonate and a huge market. I don't want to show all the field where it's used, but here is a graph that summarizes the main use of calcium carbonate. What you can see is used in paper. All the paper we are writing down is white because it contains calcium carbonate particles. In paints, now calcium carbonate is used as a substitute like titanium dioxide because of the toxic effect of titanium dioxide, as adhesive and sealant in plastic, in rubber, in building construction, and also in other fields. And this other, we will see in a few minutes, there are the fields where you can add the highest value, economical value. One can think about calcium carbonate is also interesting from the scientific point of view. Think this is I think is the second mineral on the Earth. The structure of the different polymers for calcium carbonate were established in the beginning of the 19th century, of the 20th century, sorry, around the 1906. So one can think there is not too much to discover about calcium carbonate. But this is the trend of the publication, and this is updated in January of this year. And you can see that the number of publications is increasing every year. As well, there is a constant number of new patents. So the scientific and economical interest in calcium carbonate is absolutely high. Now, I explain you that calcium carbonate can be applied by the industry in fields like paper, paint, plastic, adhesive and sealant, buildings. In all these fields, calcium carbonate is used mainly as a filler, and the cost, the additional value it can give to the material is quite low. But there are some applications, for now only potential application, where calcium carbonate can give high value. And this, of course, involves mainly nanotechnology and pharmaceutical application. This is a graph that I built up recently for a review that I'm writing. And you can see that calcium carbonate can be used to obtain helical structure between chitin and calcium carbonate hybrid materials. Luckily, this helical structure are not the same helical structure that this morning were reported by Professor Weiner. This is a composite material with high percentage of chitin, which is a polysaccharide we discuss later. Or there are studies that report the formation of hollow calcium carbonate microsphere produced from CO2, so using CO2. Calcium carbonate has been also mixed with the graphene oxide. A graphene is a single layer of carbon atoms that nowadays is one of the materials where the research is investing more. Not only, in some study, calcium carbonate can become magnetic if you put inside iron oxide. And this has been used for ultra-fast removal of heavy metal ions. Last but not last, I left here two applications which are marked by this red box. And these are where we get a contribution from our laboratories. So we were able to entrap in calcium carbonate a growth factor that could enhance bone regeneration, or we put inside calcium carbonate an anti-cancer drug, which is a doxorubicin, it can relieve, and the calcium carbonate release the drugs only in proximity of the cancer cell. Why? I think that all you know is that calcium carbonate is dissolved in acidic environments. So if we put crystals of calcium carbonate that contain a drug, they will dissolve only in proximity in the region where the environment is acid. And this is the case of cancer cell. In proximity of the surface of the external membrane of cancer cell, the pH is about 5. So in this condition, calcium carbonate dissolved and the drug is locally released. So these are some high-value application of calcium carbonate. But
can I ask a question?
Of course.
I didn't understand what are the energy application of calcium carbonate. Are those structures useful as catalysts or something else, or I missed something?
I didn't talk about this, but regarding the energy application of calcium carbonate is mainly related to the scale formation. I don't know if you know what is a scale formation, which is deposits that forms in the pipes when hot water moves in. So to avoid the deposit of the formation of this calcium carbonate in pipes, there is a big field of research because this indirectly implies the waste of energy. Okay?
Okay, thank you.
Other question? Can I go ahead?
Yes.
Yes.
Yes, please.
Okay, so I will tell you this. I give you an overview of application of calcium carbonate. But nowadays, what are the main sources of calcium carbonate? Where we can take calcium carbonate? We can have ground calcium carbonate from quarries. And this is an example of quarries where calcium carbonate is collected. And this is the main source of calcium carbonate. I think right now between 80 and 90% of global market of calcium carbonate came from caves, from these quarries. What is the feedback, the environmental impact? I think no one wants to have a view of quarry this size. And this is, with the future, will be more and more difficult to get calcium carbonate from quarry. Another way to obtain calcium carbonate is by synthesis. And in this case, there are big industries that produce calcium carbonate. The process is quite complex and involves as a starting material limestone. Then they produce calcium oxide. So basically limestone is calcium carbonate. You decarbonate by in the oven at high temperature. You remove CO2, you get calcium oxide, and then you remix in controlled way the carbon dioxide and calcium hydroxide to obtain precipitated calcium carbonate. So these are the two main sources of calcium carbonate. What is the advantage of one with respect to the other? Ground calcium carbonate, it has very low cost. When I asked the cost of ground calcium carbonate, I was really surprised. Think this, 1 ton costs less than €1. What is the advantage of ground calcium carbonate? Nature is intrinsically dirty. It's very difficult to have for quarry pure calcium carbonate. There are always traces of other ions, of other minerals. Of course, when you get precipitate calcium carbonate, you get pure calcium carbonate. But in this case, the cost increase of factor at least 10. Now, there are other sources of calcium carbonate. Of course there are. And this will be what we will discuss in the next about 1 hour at least. And the other source of calcium carbonate are shell, seashell, but not only, also eggshell. These are some of the most used waste of calcium carbonate. What is the difference between the organic calcium carbonate and the synthetic one or precipitate one? First, the amount that we can get. You can see is not the order of tens of millions of tons per year. Second, and this is the key point of my presentation, you will see later, with this biogenic calcium carbonate, it has properties that cannot be found in the ground calcium carbonate. It cannot be obtained in precipitate calcium carbonate because here the control is by the organism. There is all the biochemical machinery that is activated by the cells and end up with the production of the shells. So there is a biological control which is absolutely impossible to reproduce at industrial level or even in lab scale. As Stefano introduced, this is my research topic, but today I'm not going to discuss about this. We're going to present how waste calcium carbonate from seashell is used. Another difference that I want to stress out is that ground calcium carbonate and precipitate calcium carbonate are both made of calcite. Calcite is one of the polymers of calcium carbonate. Luckily, to the lecture of Steve this morning, that I'm citing a lot, he showed you the structure of calcite and aragonite, the two main polymers for calcium carbonate. And the calcite is obtained in the quarries and is precipitate, but aragonite cannot be obtained in the quarries and even by precipitated calcium carbonate. So the only organism can have aragonite. Now, what I want to show you, I told you that this biogenic calcium carbonate is formed under the biological control. And the biological control affects the polymorphism, but not only the polymorphism. And next slide, I hope, will be self-explaining. Here I report in this table the main polymorph of calcium carbonate, calcite, aragonite, and a third one, which is vaterite. It was not cited this morning. What we can see, that biological calcite is very common, aragonite is very common, vaterite is rare, and as Steve told you this morning, amorphous calcium carbonate is quite common. It's more than quite common. It's believed to be a precursor of all crystalline calcium carbonate produced by organisms. If we move outside of biology, so we're going to geogenic or biological produced calcium carbonate, calcite is very common. Aragonite is absolutely rare. Vaterite is very rare, but then I will tell you why I say very rare. You see, it doesn't exist at all. Dolomite, everyone knows it's very common. and amorphous calcium carbonate is not existent at all. But there is not only a difference in the distribution of this polymorph, but also in the morphology that the crystal assumes. This is a crystal of calcite from Morocco, from my personal, of aragonite, sorry, from Morocco, from my personal collection. What you can see here, the crystal, it has kind of a red-orange color. This is due to impurity that are present in the crystal. As I told you before, nature is intrinsically dirty. But this is our pure crystal of aragonite in the nacreous layer, the internal layer of a pinna. This is Altrina rigida. And this morning, Steve Weiner showed you the S structure of aragonite in a different organism. This is a crystal of calcite, also called spare of Iceland. And this is from Mexico. And here, as it appears, this crystal of calcite, you see a lot of trees wrapped by a membrane. And this membrane is an organic membrane. And this is in Mitrus californianus. I think there are no doubts about the difference in the morphology. This is a crystal of, it was reported as crystal of vaterite from Entraque, which is which is a small village close to Turin in Italy. And this is a crystal of vaterite produced by the organism. This is an otolite from the Chondrostoma nasus. This, I will tell you an anecdote now. This crystal was reported, I took this picture from the web, as vaterite. So I bought these crystals for a quite high amount of money. But then when I checked in the lab, I discovered which is calcite, it's not vaterite. So probably it was in the beginning vaterite, but with the time it converted in calcite. And now I want to go back to the structure of this polymorph, so you can understand why one phase, vaterite, should convert in calcite. Why with the time vaterite transform in calcite? To understand this, we have to go to the structure of calcium carbonate polymorph. I'm sorry I'm repeating this slide that was already shown by Steve Weiner this morning. But what you can see, this is the structure of calcite, this is the structure of aragonite, and this is the structure of vaterite. Now, let's pay attention to some details. The yellow circle here, represent the calcium ions. The red one represents oxygen, and the gray one represents the carbon. So this is the carbonate ions, and this is the calcium ions. What you observe in the structure of calcite, you have a plane of calcium ions, then a layer of carbonate ions, calcium ions, another layer of carbonate ions, calcium ions, and so forth. If we go now to the structure of aragonite, what we have? A layer of calcium ions, a first layer of carbonate ions, a second layer of carbonate ions, and then again a layer of calcium ions. If we describe the structure of vaterite, what we observe? We have a layer of carbonate of calcium ions, then we have a layer, less order, of carbonate ions, but the carbonate ions, which are planar, are not anymore parallel to the layer of calcium ions, but are perpendicular to the layer of calcium ions. These different structures have, of course, different crystalline structure, space group, but these are crystallographic detail. I don't want to go in. But what we observe, they have different solubility, and the solubility is a measure of stability. Now, we observe this data. We can see that calcite is less soluble than aragonite, and vaterite is less soluble than aragonite. So this means calcite is more stable than aragonite, and aragonite is more stable than vaterite. This is the reason why with the time, the crystal of vaterite converted in calcite. And now this stability...
Sorry, Giuseppe, I have a question.
Yes, please.
Maybe it's this, I think it's... So why, according to this scheme, try to explain again why aragonite is less stable than calcite.
Yeah. The stability is due in the packing of the ions. You can see here that each calcium is coordinated by more carbonate ions respect to what occurs in aragonite and what occurs in vaterite. It's clear now? Not only this.
Is more coordinated.
So the coordination of calcium to carbonate ions further increase the stability of the polymer. And the optimal coordination is achieved when you have one layer of calcium ions and one layer of carbonate. One layer of calcium ions and one layer of carbonate. It's clear, Stefano?
Mm-hmm.
It's not the density. I didn't correct this morning Steve, but because Steve cannot discuss about this. Because if you are looking at the density of this mineral, you can see that the most dense is aragonite.
Yes, in fact.
Calcite. Stefano?
Yes, I agree. In fact, if you look at this scheme, you understand that aragonite is more dense.
Yeah, it is more dense.
It's intuitive with respect to calcite. But then calcite is more stable.
Energetically more stable.
Energetically more stable. And you understand this from this scheme. Why? Because there is an because there is an alternation of layers, more
positive charge layer and negative charge layer. Positive, negative.
Positive, negative. Positive,
yeah,
negative.
Positive, negative, negative, positive, negative, negative, positive. It's clear?
Okay. Yes, the other one is less
less
yes.
stable because the carbonate ions are perpendicular to the plane of calcium ions, so they cannot optimize the interaction.
Okay. Okay.
But this is also important. You are going to see the density. You can see the aragonite is the most dense. Then we have calcite, and then vaterite. This can have implication in, by instance, in some studies on otoliths, because there are some fish that produce otoliths on vaterite. But I will not go this. This is not the topic of today's lecture.
Negative, positive, yes.
Okay, so going ahead.
Excuse me, can I also ask a question?
Yes, of course.
How can vaterite be converted into calcite in an abiotic condition? I mean, I get it in an organism that can decide how to organize the atoms and molecules, but in abiotic conditions, how can vaterite be vaterite at a certain point and then with time be transformed into calcite?
Of course, if you keep a crystal of vaterite in a dry condition with no humidity, with no at normal pressure and temperature, we say normal for me is ambient pressure and temperature, the crystal will remain all the time the same. But if you increase the temperature, you give a bit of mobility of the ion to the ions, these ions will start to reorganize to more stable structure.
Yeah, okay, that's clear. Thanks.
This is one mechanism. The second mechanism, if you are in wet environment, you have a partial dissolution, and of course, when you precipitate, you get a more stable polymer.
Yeah, okay.
Two are the mechanisms: dissolution, reprecipitation, or by thermal activation.
Yeah, thank you.
Okay, but today we have to discuss about waste seashell. So I told you one advantage to work with waste seashell that we can have calcite and aragonite. There are only few species that produce vaterite, and for sure they don't represent waste materials. Now, what is the amount of waste seashell produced around the world? You are working with the marine environment, so this is some of these statistics are useful to know. Here in this graph, there are the distribution of the top 10 countries in freshwater and marine mollusk aquaculture production. And these 10 countries represent 95.7% of the total global production by live weight. I stop at 10 because Italy is the last one, just to have Italy in this list. You can see that the area of each circle represent the country percentage, and that globally is about 15 million tons. This according to FAO or FishSat statistics. What you can see here, China is producing about 83% of global freshwater and marine aquaculture production. How they are distributed, these species? The majority of them are clams, pupils, half-shell. Then there is an impressive production of oyster, mussels. There is also a big production of freshwater mollusks. And you can see that the production slightly but increase along the hip. We can have a different view of this statistic. This is the tons produced every year of shellfish from aquaculture, and here I hope is more clear. You can see that China is once more winning, far away from all the other one. Then we have Japan, Korea, Italy is this red one, the United States, France, and so on. I also decide, since the majority of you are Italian, to make a graph of the national production tons, national production tons of shellfish species. This is from the year 2015, because then I had problem to access data. So around 2016, but what you can see here, that in Italy there is the main shellfish production comes from mussels, clams, and oyster is almost absent. Now, let's go ahead with this structure and start to think how we can use waste seashells from aquaculture. And this is a graph that I can try to describe some of the key processes that are undertaken during the delivery of commercial bivalves, such as oyster and mussel, from aquaculture to consumer, highlighting the points at which waste shell might be produced. So we have the mariculture aquaculture, then shell lost to the marine environment. The shell can be lost to the marine environment during sorting or harvesting. Living individuals can become detached from the growing ropes, rafts, or bags in adverse conditions, and also during the processing stage, such as size, sorting, or harvesting. Organic material decay or is eaten by shells, ash, remains, and is commonly observed below aquaculture installation. So the shells are returned to the marine environment section and can accumulate. In this case, can have a positive ecosystem service effect because they produce ground. Then, when we do the harvesting of the mollusk, we have the chain cleaning.
Giuseppe, I don't see the mouse, you know. You are using a mouse. Oh yes, now you see it.
So after the harvesting, the shell are cleaned by depuration, and then it can be sold live to restaurant or consumer in full shells. So once harvested, the product can be sold directly to the consumer or restaurant, or cleaned, processed, and cooked with shell. In this case, shell waste is spread to the consumer and is hard to recover and reaggregate in larger amount. But we can have also processing. Some products require further processing. Shocking or half shell removal resulting in clean raw shell being accumulated at processing facilities. And these are sold to the restaurant. So we go back to the case that we observed before. Or sold to restaurant consumer stack removal. Another potential processing is processing by the industry and cooking. Processing requires cooking, is usually carried out with shell attached. So basically products such as thin mollusc meat where shell are removed result in cooked and cleaned shell waste. This form of waste is mostly easily applicable to reduce because it's pure vacuum and cleaning. And this we have all the different process at which the shell can be used. And as I told you, this is where shell can be collected for daily use. Of course, there are programs that try to stimulate the attention on the potential value that seashell can have. And in this case, stimulate the consumers of the restaurant to save seashell. One of these programs I want to show you, I found on the web, has been carried out in Galveston, in the US, where there is an important use of oyster. What is done in this program? These scientists decide to involve 10 restaurants, and from these 10 restaurants, they will collect oyster shell. I want to tell you that in this period, in about 2 years, this program was able to recycle about 1,000 tons of shells. Then, when the shell has been collected, they have to be cured because they have to be dry up and to let that the remains of meat are removed by degradation or by action of some microorganism. Because the regulation requires that when the shells are recycled, since they are byproduct of food, they have to be free of meat. How is done this process? The shells are accumulated in some place, usually far away from the central city, because the shells have a bad smell. They are continually mixed, so the shell can completely dry up. After this, after 3 months that the shell are left under the sun of Texas, that should be quite strong sun, the shell can be used. They are not any more dangerous. And then the shell can be put again in the sea to build up new barriers, new reef. So this program is is now.
So what they do, they put back into the, I understand last things.
To the ocean to stimulate the growth of new reef.
Ah, okay, that's interesting.
Yeah, this is a program that it was granted by some national foundation in Texas.
You know that these things can be funded by also regional grant, probably, yeah?
Yeah, Stefan, I was studying this story when I reported this example.
I see Otello online. These things can be also in the what's the name now? The regional I don't remember the name of the funding scheme. Yeah, that's something that can be, this kind of project can be funded at the regional scale also. What's the name of the fish? I don't know. Okay.
I don't want to go too much into the detail of this project, but if there are questions, I can give detail because I studied it. And this project is carried out by volunteers.
Mm-hmm.
It's completely carried out by volunteers.
So Giuseppe, I have a consideration that is not really still more on the basic process of biomineralization. I think maybe in the future we can also try to do a seminar on basic concept mechanism of biomineralization. Really stay on the very not applied science. Yeah, no, it's okay. No, I'm saying this mollusk produce shells from the deep ocean to the tropical shallow reef into the inner lake. I mean, from very different environment from where the saturation state of aragonite is very different, because think about the saturation state that you may have in the Suviana Lake in our Apennine, which is full of big shells, compared to the saturation states of the Adriatic Sea or even more warmer sea in the tropic. So they are able to really to acclimatize the calcification process, the biomineralization process to very different environment, from warm temperature with higher aragonite state to very low temperature fresh water with almost zero aragonite saturation states. So it's very powerful. I mean, the biomineralization process is quite successful. I mean, they can use this calcium carbonate from very different environment.
Yeah, this is the key. This occurs.
It's really incredible.
If I can add the comment, Stefano.
Yes, please.
This occurs because the biomineralization in oyster, as in all many other organisms, is controlled by cells, by the activity of the cells that, of course, respond to the external environment, but they don't change completely their activity. So this is the key.
Mm-hmm.
The control is from the biology, from the cells.
Mm-hmm. Yes, okay, so please, sorry if I interrupt you, please go.
No, Stefano. So this program clearly showed that it's possible to rebuild oyster reef. And looking for this subject, I found also another quite, I want to say, exotic view. There was a paper published in Nature where a program was granted to study the possibility to make a reef to protect cities and islands. This is a view of New York that these scientists say that it can be protected by reef of oysters, And the oyster will grow on shell oyster, but not only on shell oyster, also on other substrates, because you know better than me that oyster larvae can attach on many different substrates. And they also calculate, if you think that in New York, every year, every week is discarded about 3,000 tons of glass, and only 50% of this glass is recycled. So this glass can be used for the growth of oyster reef. So there are many, preparing this lecture, I found that there are different projects that aims to reuse shell, to rebuild reef for the protection of the environment. Now, I will try to move a bit more. Stefano, it's almost 1 hour lecture. Usually you make stop, or can I go ahead?
No, we can have, if you want, we can have a 5-minute stop for a coffee when you want.
Okay, I will go ahead. You tell me when to stop. Or some of the students can tell me when to stop. Okay, now I presented the seashells, but what is the inorganic composition of seashell? And this is what you can see here. Almost 100% of calcium carbonate, which is here is measured as calcium oxide. So basically, the main component of seashells is calcium carbonate. Here you can see snail shell, cuckoo shell, mussel shell, oyster shell, pyramidal shells. In all these, there is almost 100% of calcium carbonate. But I showed you before that there is also an organic matrix. Steve this morning said the organic matrix was present in 0.01%. In some of these cases can be present up to 1%, like in oyster shell, or about 0.8% as in mussel shell, or less than 1% as in cuckoo shells. We have also other examples, but this organic matrix is the key of the structure, is the additional value of the seashells, and this has been so far completely ignored. I already showed you pictures of seashells, but now I want to spend only a few seconds on our seashell forms. What we are observing here, in this graph, what you have is a bivalve. What we have in the external layer, you have a prismatic layer, then you have a nape, the mother of pearl. And this is the mantle, and this is the peristructure. So prismatic layer, nape, peristructure, and this is the mantle. Steve this morning showed you this prismatic layer that was present in the theropods, and it was made of aragonite. In the mussels, this prismatic layer is made of calcite. There are wonderful prisms of calcite. Then we have the nacre, which is also called the mother of pearl, which has an incredibly nice structure. Here is an enlarged image of the nacre. And you can see it's made of tablets of aragonite. Here you see a different view of these tablets, all casted on the top of each other. And what is even more impressive is that the thickness of this tablet is regulated by the organism. So each species, it has its own thickness, which range between 200 and 500 nanometers. On the sandwiched between the different tablets, here represented by this red black line, there is the organic material, the interlamellar membrane. And this contains chitin and glycoproteins. But all the mechanical property of the shell came by the interplay between the crystals and organic materials. And this doesn't occur only in mussels, also in gastropods. This is a Biodiesel abalone. Also in this case, we have periostracum, the prismatic calcite layer, the nacre, and the mantle. And the growth occurs here, between the mantle and the shells. So organisms can control very well the organization of the crystalline units. So it's not only different the morphology that we observe, as I showed you before, but also the organization of crystalline units. And this, I'll give you a better view in the next slide. I hope that you understand that we did some work on mussels. This is the organization of the thin prism of calcite in the prismatic structure of the mussel, the external one. You see all this small prism? This is calcite. This is the calcite that is produced by the mussels. This is aragonite, the nacre inside. You can see now a real view, not the scheme as I showed you before, but a real view of these tablets. And between the tablets, there is organic material. I hope you can see very well the regularity of these tablets. And this is the region where you have the interface between the tablets and the prismatic. The oyster shell is not made of an internal region of aragonite and external one of calcite, but is all made of calcite. Calcite with an isomorphic substitution of magnesium, so it's magnesium calcite. But also in this case, you can see that we have this fibrous structure. This is what nature does. If we take a crystal of a geogenic calcite, like this one, and we are going to see with some technique, the high resolution technique, how is made the surface. This is atomic force microscopy. I don't want to go in detail, but this is a high magnification of the surface. You can see this is the growing layer, is completely different, the texture, the organization of crystalline units, respect to what we are observing in the organism. What is the key is that each one of these prisms, of this tablet, is surrounded by the organic matrix. This is the additional value.
Giuseppe.
Yeah?
I have a question that is possible, I think is impossible to answer. I'm sure that you ask yourself many times, but if calcite is more stable than aragonite,
yeah,
okay, so it looks like it's more, let's say, resistant to tough condition. Why the organism they do like they use different strategies? What is the meaning, the evolutionary meaning of producing aragonite, like corals? Or we also have modern corals like noctocorals, like gorgonians that do calcite. And then you have in mollusk cases of organisms that do only calcite and other that do the mix, calcite and aragonite. Well, what is the is by chance or?
I don't think it's by chance. Absolutely, Stefano, because usually the evolution is never by science.
Exactly.
But honestly, I don't know the answer. There can be different speculations. Let's say the mechanical property of the prismatic layer and of the nail are different. I think we have a paper together when we show that if we act with a pressure, one of these shell, it breaks at the interface between the two different structural organizations. So there can be a sacrificial internal layer, but this is not present, by instance, in the oyster. So it's very difficult to give you an answer. I don't know why. Honestly, I don't know. Mechanical property can be one of the advantage.
You know, once I asked Zaccanti, you know him, why the animals in shadow or dark habitats are the most colorful. You know, if you go inside the black cave, you see that there are the sponge, the corals, or whatever. They all are colored. And the answer, because there is no selection on corals, on colors. Colors doesn't matter in a dark environment.
That's true. Yeah, honestly, I don't have an answer. But I told you what. Can I go back to the lecture?
Right, please. Sorry.
Okay, so I said that the additional value is this organic matrix that wraps the crystals. And very quickly, I want to show you an image. This is not from our laboratory, but for Jean-Pierre Cuif's laboratory, which is a scientist that me and Stefano know very well. These are the calcitic prism from a pinna. I think it was Pinna nobilis. You can see all this prism. This is a top view of this prism. Okay. Now this is a fracture of this, an enlargement of this prism. You can see they grow in layers. Now, what's happening if you remove all the minerals? You dissolve completely calcite. This is what remains. You can see this is only the organic material that was wrapping the minerals. And if you remove the organic materials, what remains is the void space between the prism. But the organic material is not only interprism, but it's also intraprism. Because if you dissolve one of these prisms, and then you are able to keep the organic matrix, this is what you obtain, a sponge-like structure. So all these minerals is entrapped inside the organic matrix. Now, if we want to valorize Seashell, we cannot forget this. Now I will show you some of examples that are found from the literature on how what is the usual market of Seashell, the market that we have nowadays of seashells, and that will be the future market for Seashell. At the end, I will show you what we are doing here in Bologna to valorize Seashell. But before to do this, I learned from Steve, which is very important to give always an historical overview. So what is the historical value of shell? Historically, shell has been very important for human culture. And they were globally traded currency up to the middle of the 19th century. And the printed tools made of shells dates back of 10,000, 100,000 years ago. They were used by the Netherlands, for example. These are some, so shell have been used at least for millennia as bargain chip in China and Europe. And when metal coins became popular, they were often, shell were often reproduced on them, just to give the value of this shell. Not only this, if you are discussing about the history of seashell, they were widely used. For instance, crows cowls, which I learned this word I didn't know before. So cowl, which are these shells, were used by Chinese for trading. And you can see here they report on the top some Chinese symbols. Or, I don't want to go too much in the details, they were also used by Arabs. And this was done until the 16th century. North American natives knew of thousands of years how to work any type of shells. And they also used them as money. These are the wampum, which you can see they put fragments of shells. So shells, they have high value, and they had in the past in high economical value. Another example that I'm not showing you a picture, but that I read, in the Pacific coast of North America, they stuck shells in long rosaries, and they used for praying. So this is another application, historic application of seashells. This about the history. But what is now the current market for mollusk shell? This is a table that I took from a paper, and what you can see here, there are several large-scale markets for the valorization that are currently exploited. You can see here poultry, feed, pet bird nutrition, biofilter medium, aquarium, pond pH buffer, soil lining, shell aggregate. And this is usually the quantity sold for package, and this is the selling price. You can see the value is quite low, but it cannot be high because it's waste material. In any case, the scientists are recovering this waste material. Where these applications are possible? Generally, this application has been established in areas that generate large amount of seashell. An example of this is the production, is the use, the continued use since several years of master shell in Galicia, in the north of Spain, because this is one of the regions where there is the highest production of seashell from aquaculture. As I highlighted here, the main market for mollusk shell is livestock feed supplement. And this is what I'm showing here. Several organisms, like herons, have to use calcium carbonate in the diet. And this I want to report here some of the statistics. It's not a really close statistic, but it's quite interesting to have this number. In 2011, there was a population of 363 million line ants in Europe. Now, line ants require about 2.5 grams daily of calcium, with a rotation rate of about 50%. So they need a huge amount of calcium. And this calcium basically is spread out. It can be supplied by crushed shells. I remind you that if we take 100 grams of calcium carbonate, there is about 40 grams of calcium. So 40% of the amount that we are providing is made of calcium. Here we have 3 examples of what I found some realistic scientific literature on the shell as calcium supplement for livestock. What found some researcher, you can see the journal where it's been published is not at the top impact journal, that the addition of shells to limestone supplement significantly improve egg production of line hens. Some other scientists observed that oyster shell favored the growth response of eggs. So they got eggs of bigger size. On the other side, another paper discovered that basically there is no difference in using marine shell derived calcium carbonate of mined shell from quarries. So the literature is quite controversial. One thing that has to be considered when we want to use waste seashell as livestock feed supplement is that the shell, as I told you before, they have to be free from flesh, so free of meat, because they are classified as animal byproducts. And this is a big limitation in the application of Seashore, because this, to remove the remain of meat, it has a cost, or at least it requires a place where this material can be stored for a long time under the positive effect of sun. An interesting paper that I observed, that I found in the literature, consider another aspect that is of general interest for recovering seashell, a mollusk shell. And this is, the title is already explained, making the best of a pest. That when I read for a chemist, I said, what means this? The potential of using invasive zebra mussel biomass as a supplement to commercial chicken feed. So in this topic, I think you know much better than me, but zebra mussels was is native from Black and Caspian Sea, then was introduced in North America, and when introduced in North America, zebra mussels caused significant harm to freshwater ecosystem because it became outcompeting with native species. So the zebra mussels has to be removed. And not only this, zebra mussel can also dog water intakes under the pipes and attach themselves to both motors, wood, and docks. So they give a lot of problem. Now, one way to recover this zebra mussel is to convert in feed for animals, for chicken or hens. And this is what was done. It was shown that the hens that were fed with this shell increased the production of eggs. Now, I don't know this how much is used, but this is true. But this is at least an application that convert a pest in a best. This is the main field of application for mollusk shell. Then what we have? Soil liming. So this is the second major market for shell, which is in agriculture. And what means liming? Which means reduce the acidity of contaminated soil. soils. And this acidity usually came from metal ions. This is very old procedure, is known from years, and historically goes back to the 1st or 2nd century before Christ. One of the problems that can be encountered when we use seashell is the presence of sodium chloride, because seashell contains a small amount of sodium chloride, and this is a problem for this application. So we have to pay a lot of attention on the presence of sodium chloride. In any case, there were studies performed on garbage that showed that the sodium chloride is not a problem at all. Sì, scusate.
Allora facciamo
sto facendo una
mattinata, sei libero?
Domattina sì, va bene.
Vabbè.
Sorry, someone got in my office without knocking the door. The presence of seashells can be really effective, but in the majority of the case, and you can see here from this diagram, seashells or waste biogenic calcium carbonate, here are eggshell, are not used as produced, but they undergo to calcination, then they do land application. In this case, you have soil neutralization. So they convert, as we observed before, calcium carbonate in calcium oxide. And this is a problem. This is an economical problem and reduce the application of calcium carbonate as liming agents. But in any case, the effect is quite impressive. You can see a field that was untreated, and this is a treated field. Has been shown quite clearly that there is a correlation between the amount of seashell which is added to the soil and the pH of the soil. You can see that increasing the amount of seashell, there is also an increase in the pH of the soil. Is this economically sustainable? It is an advantage. Honestly, I'm not able to make this kind of evaluation, but we have to think that all the process that brings to the formation of calcium oxide. So, seed production, oyster cultivation, consumption, oyster shell waste, and not oyster processing, treatment, calcination, and then you get raw calcium oxide material that can be used. Of course, this raw calcium oxide material you can get directly from calcium carbonate from mining, but this has the negative effect that I already discussed before. Now I want to show you another paper in which is reported the pH-dependent copper release in acidic soil treated with crushed mussel shells. So basically what this researcher did, they used directly mussel shells, no calcium oxide, no treated, because in this case we are going to lose the advantage of the mussel shells. So what they did, they hardened the mussel shells, and then they followed the change of pH by adding an acid or a base. And what they observed that in the presence of mussel shell, the change of pH adding an acid is drastically reduced. While when you add in the basic pH, you have a less effect. Another study that was performed in Galicia, in Spain, found that mussel shells are able to remove from the ground arsenic. Why there is this interest in copper and arsenic. Why these two metal ions? Because copper is widely used in vine farms. So these are the main applications is agricultural liming agent. But seashell can be used also in construction materials. Also in this case, the application of seashell in construction goes back to the history. These are some ancestral temples in China from Ming dynasties. This is a toby, which is a material that was developed in North America, and is basically a mix of lime, oyster shell, and water. And this is now a modern structure in which was used oyster shell. How oyster shell are used? Usually they are used as aggregate, so they substitute the aggregates which are in the mortar mixed. Also in this case, there are several studies, and here we can see I reported 3 of them. A study tested the large and small particle of oyster shell, and they mixed with the sun to make a common mortar. And it was found that the particle size is a key parameter for increase the compressive strength of the mortar. Another study didn't take in consideration the particle size, but consider the microstructure. So they took shell with different microstructure. This is the big advantage of the shell, that we can have a long scale of different microstructure. We saw cross-lamellar this morning. I saw you fibers. We can see prismatic structure, nape. In this case, it was found that the prismatic structure of the mussel improved the setting time of the mortar. And of course, the third example that I show is, of course, before, is a study that is contradictory with the previous one. Indeed, in a different study, they observed that the addition of grounded mussel shell doesn't have any effect on the properties, on the mechanical properties of the cement, but it can increase the water permeability. And this can be an advantage for some peculiar application. I was telling you that mussel shell improve the setting time. It's also called curing time. And this is what was found using different kind of shell. Just a short window in cement. I don't know if everyone knows that the setting time or curing time of cement is 28 days. So basically, the cement, to reach its optimal mechanical performance, requires 28 days. During these days, what's happened? That the cement absorbs water and convert silicates in other mineral phase that interlock among them and provide mechanical properties. An additional information in the cement, there are about 22% of water in mortar cement. What you can see here, that different shells and well used, and you can see that 7 days and 20 days, the compressive strength in some case was almost the same at 7 days, so you don't have to wait 24 days to have the cement providing the best performance. So the use of oyster shell reduced the curing time. There is still some student. I didn't hear any question more.
Yes, we are here.
So you want to make...
Giuseppe, I have a question, but the idea here, in your opinion, is to recycle the shells or to produce cements that have similar characteristics like the cement with this additive, or both? I mean, my question is to recycle or produce a cement with these characteristics, or both?
Both, but the problem is the following. If you don't use calcium carbonate from seashell, you have to use calcium carbonate from quarries. And it has, as I said to you about 2 hours ago, a strong environmental impact, okay? You are using a waste. So the idea of cement company is that even if you get the same performance, is already an advantage because you are using waste. And I don't know now the European laws, but I think that the companies are obliged to increase the recycling process of their product. And one of the ways is to use waste.
Yeah, yes, and the waste material, the amount of waste material can actually support an industrial production of these kind of cements.
Yeah.
It's enough.
Yeah, it's enough, it's enough. I told you which amount I produce. Okay, do you want to make 5 minutes of break?
It's to you the question, student, not to me. I'm
As you
alive.
prefer.
Yes, it's fine.
Okay, 5 minutes. Okay.
Okay, we see in 5.
Stefano, can we start again?
I don't know if they are here. Let's wait another minutes, Giuseppe.
Okay.
Thank you. I guess we can restart. First of all, I want to remind everybody the program. Tomorrow morning at 9 o'clock, we have Felicia Dinolfi. And then Thursday afternoon, we have Jacopo Aguzzi. And then Friday morning, we have the last for this year, Zvi Dubinsky from Bar-Ilan University, Israel. Jacopo instead is from Spain. I also I wish to thank last night Matteo, I guess, that he closed the lectures. I was absent. Yes, I informed actually my colleague. I thought he would tell you that I was not present in the second half because I had a department meeting that started 4 o'clock and finished 4 hours later. So that's the reason why I was not there yesterday. At the end, as usually I am instead. So Giuseppe, if you want, you may go on, I guess.
Okay. So first, as first thing, I want to ask if there is any question by student, because I spoke already a lot, so. Okay, no question, I will go ahead. So, another field of application of waste seashell can be separation of pollutants from water and air, as I reported here. And in this case, there is a quite spread literature and some current real application. Here I reported you some example, by instance, to remove copper from water, to purify acidic mine damage. It's been used also to remove dyes or to remove acidic gases like sulfur and nitrogen gases. But a large portion of this research does not use shell directly, but they use shell after calcination. So basically, they use calcium oxide instead of calcium carbonate. And this is a limit because seashell should be used as they are as biofilters and not a derivative. But why the majority of research is performed using calcium oxide instead of calcium carbonate? And here, what I'm showing you are the usual shells, but these particles, this is calcium oxide that has been obtained using waste seashell. And what is the advantage? The advantage is the presence of pores. When you remove carbon dioxide from calcium carbonate, you generate pores, and the porosity that is obtained by seashell is higher than the pore that we obtain using geogenic calcium carbonate. So the efficiency that you have in remove pollutants is higher than we use gravels, by instance. But what implies the fact that we use calcium oxide implies what we observed before. So we have a step, and in this step we have to convert calcium carbonate in calcium oxide. Then you can use this material to purify air, for instance. Everyone of us knows that air is the key component for biological life. So all the gas which are emitted by industry should be, of course, not polluted, but also we want also gas that are odorless. This is to avoid the nuisance. And the common odors came from ammonia compounds and hydrogen disulfide, and all sulfur compounds. For this, what you can see here is a schematic that has been engineered in Japan, and how it works. This is the system where it ends. You put in polluted water, then you have a column of crushed shell product, so basically calcium oxide. You put water from the top, the gas moves in, the water follows the interaction between particles and the polluted gas, and then you get with the polluted air. Of course, the water then can be recycled, and at the end, part of the water is pushed away. So this is a mechanism to clean up air using calcium oxide from seashell. But I told you, we can also purify wastewaters. And this is an interesting example where it was not using calcium oxide, but powder shell in Aragonite polymer. And then now if we go back, do you remember what is the difference? One of the main differences between calcite and Aragonite, which is the thermodynamic parameter that differentiate calcite and Aragonite. This is a question for the student.
You mean the solubility of Aragonite?
That's right, the solubility. So what's happened? Aragonite is more soluble than calcite. So if we take fragment of seashell and we treat with in waters, this can be rather clamshell or oyster shell. Now, second question is written here, but I hope you remember that oyster is calcite, not aragonite. Okay, so we can see that the rather clamshell performs along the time better than oyster shell. And what's happened? That during the process of purification, calcium carbonate dissolve and reprecipitate in the forms of carbonate of different ions. This means lead carbonate, cadmium carbonate, or zinc carbonate. So on the surface of the shell, it forms different carbonate. And this can be seen by the X-ray diffraction patterns. This is a pure aragonite. This is the different minerals that form from lead, cadmium, octavite, and zinc. And you can see that the signal, distribution of signal change, because when this particle interact with these ions, convert from calcium carbonate to other carbonate. Is clear this?
Yes.
Yes. I have a question.
Yeah.
When the aragonite becomes saturated with these pollutants, how then you dispose of the material to use a new one for purification, and then you have to dispose of the old one that you used?
Yeah, this is an interesting question. Usually what they do, first of all, they try to use grain size as much as possible. You can see on this SEM image that the particle deposit on the surface. Can you see?
Yeah.
So if you use small particles, let's take as example only lead. Here it forms lead carbonate on the surface. And with the time it increases the amount of lead carbonate it forms. Then at the end of the process, you have purified the water from the lead, from lead, and you have basically calcium carbonate in the form of aragonite and lead carbonate. Can you follow me so far?
Yeah, sure.
Now, if you dissolve this mineral phase, you can recover the lead. So it's not only a way to purify water, but also a way to recover lead.
Yeah, okay.
This is another example where is shown the effect of pH for the absorption of cadmium on a freshwater invasive snail, which is the Pisa acuta. Please forgive my knowledge of zoology. But this is another example of invasive species, like I showed you before with the zebra. And what this study showed here, that according to the pH, the capability of the substrate to absorb cadmium from different environments change. Of course, in the acidic environment, the uptake is lower. When we increase the pH, you can see here that we have a higher efficiency of absorption of cadmium as milligram over gram of sugar. Then the study was done also as function of the cadmium concentration in solution, or the amount of powder seashell used. And you can see if you increase the amount of powder seashell, also it increased the amount of cadmium uptake. This is what you can see here. There are two spectrum. These are FTIR spectrum, which are quite similar to Raman spectrum. So basically we have the molecules are excited by light, specific light, and then when they relax, they have some specific transmission bands. What show this spectrum, without going into detail, that in this case, cadmium is mainly linked to the organic matrix of this shell. So the advantage of use a seashell, in this case, sorry, freshwater shell, but is also use a biogenic calcium carbonate, is in the capability of the organic matrix to interact with cadmium. So this will be not possible using geogenic calcium carbonate. Now, moving on the application that have already a market, a big market is the use of calcium carbonate as filler in polymer. And now I have also a project with a company that is trying to use waste calcium carbonate in polymers to improve, at least to improve the mechanical properties of the polymers, but also to go inside the discussion that Stefano showed about the possibility to recycling materials. Now, I am reporting now a study in which master shell, grounded master shell, were added to a polymer. In this case, it was a polyethylene. And what was found that this is the X-ray pattern of a master shell, and this X-ray pattern show the diffraction peak of the two phases that now we know are present in the master shell, calcite and aragonite. But as you already learned from this morning, is the percentage of calcite and aragonite is not constant in master shell. It depends from the site where the shell were collected, but also from the age. This is a study that now we are performing with Stefano together. So they use different mixture of mollusk shell, and what they observe that if you increase the content of mollusk shells, and then you are going to measure one parameter of mechanical property, which is the fractional model, how much the material became hard, you can see that increasing the percentage of mollusk shell, the mechanical property, increasing the percentage of mollusk shell, the mechanical property increase. Not only this, I'm not showing here the graph because it's a bit complex, but they also show that there is a real interaction between the mollusk shell, organic matrix, and the polymeric chain. So this basically means that these materials, when you use biogenic calcium carbonate, is not only a filler, a simple filler, but it has additional property because it can interact with the polymer molecules. And this is the path that everyone should use to valorize to valorize calcium carbonate from waste seashore. Now, in the next slides, I'm showing you some potential and unrealized application of mollusk shell. These are applications that can be seen in the view of wide market application. And maybe it can appear a bit exotic. One potential application is as de-icer grit. I think that every one of you knows that when there is even a small amount of snow, ice, or frost, having surface can become impossible. So a common strategy in this case is to add chlorine-based rotting. But this is very detrimental for the urban environment and for the natural environment. Besides this, these road grids are widely used, but not in the airport, because the sodium chloride, the chloride ions basically, have a corrosive effect on airplanes. So, a potential application of waste shell is in this field. And there are already some studies where they show that ground calcium carbonate can be used as de-icing agents. Another apparently exotic potential use of mono shells is as green roofing substrate. I'm showing here some image of green roofing substrate. Why this is becoming more and more popular, and I think now in all architectural view of the city of the future, we have some roof with plants, gardens, and all kind of agricultural activities, I would say. And in this case, it has been reported that the use of waste seashell can have great advantage because it can improve the permeability of the roof and reduce the retain of water. And all the other advantage that I illustrated to you before when we discuss about lining and water purification. Another use is shell that are returned to the environment, but not for the growth of oyster reef, as I showed you before, but to have an ocean alkalinization. We know that right now, when the CO2 goes in the water, CO2 converts to nitrogen carbonate and reduce the pH of seawater. So there have been studies where they claim that if we use calcium oxide, not calcium carbonate, and this calcium oxide goes in the water, it can reduce the acidity of the water. Of course, this effect is more local than on the wide scale, because it's very difficult to think a global scale application of calcium carbonate from waste seashell to reduce the acidity of seawater. Another potential application I showed you before in the program in New York, it was in New York or in this in Texas, is to return the seashell directly to the water. This I already discussed this, so I will leave here this slide. I will not go in because I already spoke about this. And I don't know, Stefano, I wrote a lot of notes on the slide because I thought that the slides are going to be provided to the student. Is this true?
Yes.
So for this, it will remain some things written.
Yes. I have a question. Is if you put calcium oxide into the water, how can you reduce the pH? Because no, reduce. Sorry. How can you reduce the concentration of hydrogen ions with calcium oxide?
Sorry, I forgot to say some chemistry. Calcium oxide in water converts in calcium hydroxide, which is one of the strongest bases that exists among chemicals. And so it neutralizes the acidity.
Okay.
Okay, Stefano?
Yes.
Okay. There are potential.
So I can say something. Basically, Because when you actually produce calcium oxide from calcium carbonate, you remove CO2 from calcium carbonate, right?
That's true.
So basically, it's a kind of producing CO2, and then it's a kind of circle.
Yeah, for this I was quite skeptical about these studies. Even it's been reported in the literature.
And also I have another, maybe they can attach, like a connect photosynthetic system when they produce calcium oxide from calcium carbonate. So they use the CO2 to produce sugar.
This could be an interesting...
We need Svidubinski here.
So I think in 2 days there will be the seminar of Professor Svidubinski on algae, no?
No, because when you actually take out CO2 from calcium carbonate to produce calcium oxide.
This is absolutely true, but what they think, I didn't go too much in detail, this calcium carbonate, this calcium dioxide can be used with the catalyst to produce what is called syngas, which is the conversion of calcium dioxide in ethanol, basically. In methanol, sorry. So for other chemical process, it's quite difficult to believe, but carbon dioxide, CO2, for some aspect is a big problem because we don't want CO2. But on the other side, if we have pure CO2, it has a value. Okay, Stefano?
Yes, it actually can be used
in the atmosphere, in the mix with all other gases on the atmosphere. This is a problem. It's an environmental problem for all the global warming effect, ocean acidification, and so forth. But if you have pure CO2, it has a value. Okay, so there are reported applications of waste cell derivative as a catalyst. What means catalyst? I hope you know. The catalyst is a component in a chemical reaction that make the chemical reaction faster. And there are several examples, only reported in the literature, no industrial application, where they show that to use calcium carbonate or calcium oxide from waste shell give better performance compared to the use of geogenic calcium carbonate. This is a list of literature that you can check by yourself, but I will show you only the most representative example. Now there is a big interest in biodiesel, so the conversion of oils in fuel, oil from agriculture, and you can see here that they show that this process can be favored by the use of waste shell. There are also trans-esterification, production, lithium, battery, separately. You can see the biodiesel is the main, is the goal, but not only this. Also production of chemicals like aldehydes and ketones, which are of interest for the industry. Last, but not least, is in biomedical application. As I told you at the beginning of this lecture, when we move in biomedical application, the value increased drastically. Why? Because we pay a lot of money for our health. So what is been shown here, that waste calcium carbonate can be converted in ceramics calcium phosphates, that are here indicated, which have a structure similar to that present in bone. These ceramic of calcium phosphate are made of a mineral called hydroxyapatite. And these are the appear the particle of hydroxyapatite that are obtained from seashells. And this is how it is a bond. You can see that in both cases, there is a bond structure that can be colonized by cells, and then the cells can reconstruct the bone. I forgot to put here, but there is a paper that appeared about 10 years ago, which was called A Marriage Between Corals and Bone, because some scientists used corals that you should know already, that have a high porous structure, to reconstruct a bone. The way of application of waste seashell, of course, are different. In some cases, they are grounded and then converted in hydroxyapatite. In many cases, ground seashell are used in combination with biodegradable and biocompatible polymers to produce composite materials and improve the mechanical properties. But there is the possibility to convert waste seashell in bones. Now, this is the last example of a potential application from the literature. But I told you that also in Bologna, we are trying to develop a project for shell valorization. This is a project at which a PhD student of mine and Stefano is working, is partially working, which is Carla. And this project, we want to convert seashell in products with higher value. And one issue that we face is the following. We want to preserve the texture and the content of the organic matrix in seashell, because I showed you so far that all from the literature data or from the real application, when we still have the organic matrix, we can have real advantage respect to the geogenic calcium carbonate. So the first issue that we have to face is to produce particles of a small size that still preserve the organic matrix inside. And for this, it's important to develop a milling strategy that is based from a crushing mill that we have now, a quaternary mill, and analytical sieve. And if you do all this process, at the end of this process, you can get with a particle size distribution that can be of few micron or below the micron size. These are additives that are used to favor the grinding mill. But this is the particle size. And I told you that by instance, that when you use seashells in cement, if you reduce the particle size, the mechanical property improves. But in this case, we are not going to use the organic matrix. Now, what we are showing here in this image is that if we have particles of biogenic calcium carbonate, these particles expose the organic matrix, and the organic matrix has some functional group. This is the carboxylate group in its acidic form. This carboxylate group can link a dye. This is a rhodamine, which is a common dye, and linking the dye, it can form a bond, chemical bond. So in this case, you can increase the amount of dye which is linked to the particles. This is a particles of a grounded oyster shell in which the dye was only absorbed, and this is, and here we have particles of grounded shell in which the dye were chemically linked. I think you can see by naked eyes the difference in color testify for higher content of dye in this material. So you can get a calcium carbonate with a different properties, valorizing the presence of the organic matrix. So in conclusion of this first part, but the second part will be much shorter, don't be worried, of my talk. What we can say? In mollusk aquaculture, I showed you at the beginning of the talk, shell waste remain a barrier to a sustainable growth. And we know that shells are in majority calcium carbonate with a small amount of organic matter. So we have to valorize shells in the field where calcium carbonate is used, taking advantage of the small amount of the organic matrix. I show you some example, even exotics, like the use of seashell as eco-friendly deazer substance, or in a green roofing structure. Of course, there are many other processes where they can be used, but it's important that the potential of use waste shell doesn't require the high energy processing for pyrolysis or decarbonation. It will be also important to use shell in proximity to the site where they are produced. This makes all the process more sustainable because, as I told you, seashells have to compete with the calcium carbonate from quarry that it costs less than €1 per ton. It is also to be considered that if we reuse waste calcium, waste shell, this is where we not disposed in the landfill, and this can have positive effect on the environment. So what I want to conclude in this first part of my talk, that shell is not to be observed as a nuisance waste product, but is a valuable commodity that could provide economical and environmental benefit is utilized correctly. Now, this is the end of first part of my talk. And now I want to talk a bit about chitin. I said to you that also chitin is a byproduct of the fishery and the shells and can have many industrial uses. In this case, I will go a bit more in the chemical details, and I want to show how we use chitin in our laboratories. Since your background is not a chemist, I will make a very preliminary introduction on chitin. Can I go ahead?
Yes.
Yes.
Question?
Yes.
Okay, what is chitin? Chitin is the polymer of is a polymer based on a saccharide, which is the N-acetyl D-glucosamine. The glucosamine is this functional group. Now, if we remove this functional group, we can see we got from NHCOC, CH3, to NH2. This is the monomer that made chitin. And this, the D-glucosamine, is the monomer that made chitosan. So what is the difference between chitin and chitosan? The presence of this functional group. So in the polymer of chitosan, here we don't have COCH3, but we have NH2. In nature is present chitin, but there are about 10% of free NH2 groups. Now, when the percentage of NH2 group is higher than 65%, the material is referred as chitosan. If the percentage of N-acetyl D-glucosamine is higher than 35%, we talk about chitin. Chitin exists and is in different polymorph. You already know this word from calcium carbonate. This means different organization of the polymeric chain. In the arthropod exoskeleton, in the majority of Piccola, in many organisms, chitin is present as alpha chitin, which means that the polymeric chain are anti-parallel. You can see one chain goes in one direction, another chain goes in another direction. In the beta chitin, all the chains are parallel. This is the case that we'll investigate a lot of l'oligo squid pen, the pen which is inside the squid. There are some cases, very rare, like in the cocoon or this butterfly, which is the Orgia dubia, in which chitin is organized in two chains parallel and one chain anti-parallel. And this is called gamma chitin. But this is quite rare, so we'll not consider at all. Sorry, a bit more of chemistry, but not too much. What's happened when we compare the structure of alpha chitin and beta chitin? Now, I will go ahead. Pay attention to the polymeric chain. These are the polymeric chain of chitin. In alpha chitin, I told you they are anti-parallel, where in beta chitin they are all parallel. This dotted line, dotted red line, indicates the interaction between the chain. What you can see that in this direction, alpha chitin, it has interaction, the alpha chitin chain interacts, where the beta chitin chain, they don't have any interaction. What means this? That beta chitin are much more, are less stable compared to alpha chitin because there are less chemical interaction. So it can be modified easily compared to alpha chitin. But chitin is really abundant in nature. Is present only in marine environment, also in other environments. Now, some statistics. Chitin is a polysaccharide, and it has a structure which is very similar to cellulose. If we are considering now the annual production of chitin by the organism, is between 10⁶ and 10⁻10 tons per year, while cellulose is about 10 and 12 tons per year. So the amount of cellulose which is produced by the organism, by the plants, is much higher compared to the amount of chitin which is produced by organisms. But now, if we are going to see the distribution of our species, chitin is present in over 70% of known species, while cellulose in about 15%. So you can really feel how much is spread chitin. In the majority of the chitin is present in many marine organisms, but not only many organisms. And even when it's present in an organism, chitin can support different functions, not just one function. Now we'll show a video. This is a study that a very brilliant student that was working in my lab, which is Davis Montroni, did. Davis already, I have to say, also did a diving course with Stefano, so Stefano also knows him. He decided to study the buccal mass of a slug. This slug is the...
David Montorsi?
Montroni, yes.
Montroni, yes.
Yes, was also your student, Stefano?
Yes.
So he decided, he's very brilliant student, and you remember what Stefano said, what this morning Stefano and Steve said. If a student has an idea, he has to perform his idea. If it works, maybe he can provide interesting results. So he decided to study the buccal mass of this slug, the Adenomax californianus. And you can see what's happening here when this organism is eating leaves here. You can see he opened the mouth, an organ came out, and then he grabs the leaves. Now, if you are going now to study the mouth of this organism, the buccal mass, what we have basically are three tissues. The jaw, here indicated by one, the radula, and the odontophore. But what is critical, that in all these three tissues are made of chitin. The main component is chitin. So this is really an example to show you how organisms use chitin to build up all this buccal mass in all three main components. I don't go into details of this study because it's not the topics of this study, this presentation, but what I can show you also is that chitin is not only used in mineralized structure like seashells. I told you that the nape there is chitin, also in theropods that Steve was showing this morning is chitin, but also to produce photonic materials. This you can see, this butterfly has the capability to reflect light, physically light, in this light blue, or these bugs that has a gold surface, and this is due to the specific structure of chitin or the enhanced mechanical property. This is a mantle stream which is able to break master shards. Where it comes, these peculiar properties? It comes from the textures. This is a mineral structure. Here, the mineral, all this mineral organization is governed by the chitin framework. And the mechanical properties, we come back a bit to the lecture of Steve this morning, is done by the rotation of the chitin fibers. As you can see, these chitin fibers are not all in the same direction, but are rotated, and this support the increase of mechanical property, because the load is released among the layers. And even when you have photonic crystal materials, this is due because the space between the chitin fiber is of the same order of magnitude of the wavelengths of the light. So, how chitin is produced? Chitin is produced by in biochemical apparatus where you have some organelles that are called chitosomes. The polymer chains produced by these organelles, they are extruded by the cells, they are released extracellularly, and then they assemble to form chitin nanofibers, the one we saw here. This assembly of a chitin chain in chitin nanofibers is governed by proteins, by the pH of the environment, and by the presence of specific ions. One of the questions that we try here to address is how these complex structures develop. And we use as a model system a waste material. So we go back to the waste. This is the squid pen, which is the internal gladius, which is inside the squid. I hope that I think that every one of you knows this material. At least every one of you had some in his life, he ate some squid. And this has the support to anchor the organ, also to protect the organ from undesired bending. how is made this pen, squid pen? So there are nanofibrils of chitin that are produced by the chitosomes. Then they assemble in microfibers and start to be wrapped by protein. They assemble even more, always with protein wrapping, until you get the final product. So it's an hierarchical self-assembly of fiber units. And this is what provides this hierarchical self-assembly the additional and relevant mechanical properties. So this is a composite of chitin and protein. The amount of protein at the end of the process is about 60%. Now, can this be this composite modified? Can we change the mechanical property of this material and then maybe we give a potential use of this waste material in fields where a different mechanical property are required? One of the fields that has been published by our group for the reuse of this material is as a substrate for cell growth, by instance. Okay, how we can modify the mechanical properties? Now, a bit apologize, this graph is too much, in this slide is too much chemistry, but I told you the squid pen is a composite of chitin and proteins. And I hope it's clear now to all you that the proteins wrap the chitin fibers, so the self-assembly process is governed by the interaction between the proteins. Now, how we can modify the mechanical properties of these materials? By different chemical treatment. What we have shown here in this table is EDTA, Merck, urea, mix-24, mix-48, enzymes, NaOH, NH are different chemical treatments. Each one of these different chemical treatment affects different the interaction among the proteins. And how we can study this interaction among the proteins? By infrared spectroscopy. So the same techniques that I illustrated before. So we know how much change the interaction between the proteins. What we can see also here. Let's focus now on this last column in this table. This is the swelling. So we start from dry squid pen, and then if we put in water, how much it increases its weight absorbing water. And of course, how much it will increase also its volume, not only its weight. What we can see that according to the different treatment, we have a different swelling. But if the substrate swells, this means the interaction are weaker. So more it is well, weaker are in the interaction between the fibrils of chitin. Is clear this concept?
Yes.
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 Now we go to the second column. What we can see, the first one basically is a color, so just to identify that after some treatment we lose the organic materials, and then we lose the organic proteins. And when we treat with sodium hydroxide, NaOH, we lose almost all the protein. It's about 60%. Told you that the amount of protein is about 60%. And this process can be followed either by weight loss, so basically we are weighting the squid pen after each treatment, or by some spectroscopy. When we lose material, we release some proteins, and this is the gel electrophoresis of these different proteins which are released. But a key issue is the structure, the overall organization of the chitin fiber changed, because we know that mechanical properties are related to the overall organization of the chain. So if in this process we are going to change the overall organization of the chain, of course we for sure we will lose the mechanical property. How we can check at the micro scale, at the subatomic scale, the organization of the chain? At the macro scale, doing SEM image. We don't have, unfortunately, in Bologna a FIB SEM, the one that was shown this morning by Professor Weiner, because it is an instrument that costs almost €1 million, and unfortunately we cannot buy it here. So we have a conventional SEM, so we cannot reconstruct the 3D structure of the squid pen, but we can see that in the majority of the treatment, this layered structure is preserved. And even if you are going to see this diffraction pattern, we can, and please pay attention to these arcs. This is an index of how much the orientation of the fibers is high. Smaller is these arcs, and higher is the orientation of the fiber. This is the original squid pen, and you can see that if we consider these arcs, and we measure the spread of this arc, after the different treatment doesn't change too much. So the orientation of the fibers of chitin remain the same. So basically what we change is the interaction between the fibers. And what we observe when we measure the mechanical properties, that according to the different interaction, we can have a different force profile. This is a curve in which we report the stress, which is the force that we have to apply to obtain a deformation, which is the strain in percentage. This, what means this, the red one, which is the squid pen. You can see we have to apply a lot of stress, of force, to get a small deformation. And after we reach this limit, the squid pen breaks. On the other case, after different chemical treatment, we can see that we can change this profile. If we now consider the green one, what's happening? You can see with the minimum stress, we can get a significant strain, and also the maximum strain that we get before the sample break is much higher. So with this system, we were able to control the mechanical property of the materials and also the degree of swelling. Why is important degree of swelling? Because if we want to use this material for high value application in biomedical field, the cells has to be able to colonize the system. So we need an open structure with a lot of water inside. So now we know, according to the chemical treatment, how we can convert the squid pen in a material with the different mechanical properties. Okay, this is a graph that summarizes what we observe. Okay, now we know now how to change properties of the squid pen, but as chemistry, if we want to do some things more, to give a value to this material, what we can do, how we can valorize even more this. One way is to modify the structure. And now I have to go back to this slide. You can see here we have NH2 group and OH group. This chemical group can be highly reactive. So the chemist can link to the NH group other chemical functionality. And if we link other chemical functionality, which is not the one that reproduces the chitin, but different one, we can give to the system different properties. So if we want to work with systems that is with a system which is inspired by nature, we have to go to observe which functional group nature can provide us. These are mussel shells, and you know what is this? Some of you have ever collected a mussel in this life?
You must know, guys, what is.
Bissum.
This is the
Right.
byssus. Perfect. This is the byssus. I think that every one of you knows what is the byssus, but I think that few of you knows that the byssus is a polymer, a natural polymer, which has the highest mechanical performance on the Earth. Not only among natural materials, but also among synthetic materials. So the mechanical, and you know which polymer is used to make sails. Yeah, you should be more confident with boats than me. Someone of you knows the word Kevlar. You never heard?
Yes.
So
Yes.
Kevlar is the
Yes.
synthetic polymer that has the highest mechanical performance. But what is that? This is one of the black side of the or dark side of the Kevlar. When it breaks, it breaks in a catastrophic way. So it doesn't have any self-healing properties. On the other side, the byssus from the mussel shells, it has self-healing properties. Why it has self-healing properties? Because the molecules in the byssus coordinate, these molecules coordinate in iron 2 ions. And this coordination bond can break, but if you release the strength, it reconstructs. So it's a self-healing. So if we are able to move this functional group in other system, maybe we are able to obtain a polymer which increases the mechanical property or which has mechanical property similar to those of the byssus, and the final goal should be to get a polymer that has self-healing properties. So if
Where is now, Dennis?
Davis is now in Irvine,
Where?
California.
He's still in Bologna? No, he's out. He's abroad, I understood, no?
Yeah, I told you, he's in Irvine, in California.
Ah, okay. I didn't understand.
Irvine is a city close to Los Angeles.
Okay.
So if we are able to insert this functionality in chitin, and then we put iron, we should increase the mechanical property of chitin. You agree, guys?
Yes.
Yes.
So we can be bio-inspired by the mussel byssus, and then we can make this what we call top-up approach to organize chitin to functionalize in the already hierarchical organized chitin matrix. Now, these are all the chemical reactions that were performed. I don't want to go into the details of this chemical reaction, but you can see at the end of this chemical reaction, we get a substrate which is able to link iron as it occurs in the byssus. And now it comes to the difficult part. it really works, this, or is just fiction. So first of all, what we did a lot of chemical tests. So this is the substrate. Then we had the functional group. This is the piece of squid pen. This is a piece of squid pen that has been functionalized. Then we put iron. And you can see what's happened when we put iron. The color of the strip of chitin changed drastically, because when iron links this functional group, the color changed. It became this dark blue. These are some spectra. This is Raman Spectra, one that Steve showed you this morning, and these bands testify that this complex is formed. But then what's happened? If we treat with EDTA, which is a common chelating agent, so it's something, a chemical which is able to sequestrate iron ions, we can remove iron from this strip, and you can see the color goes back to the original one. Then what we can do? We can go even further than what nature does. We can do some oxidation process of this functional group to make a chain, so a polymeric chain. And also this process is associated to a change of color. But in this case, we are not making a chemical bond like this, that you can break and rebuild. You make a chemical bond, a covalent chemical bond. So you cannot break, and rebuild. So there is no way from here to go back here. But then we test if it's possible for this substrate to absorb iron. And since there is still this functionality which is present, iron can be absorbed. And of course, if we treat with the DTA, the color goes back to the pristine, the previous one. If we, of course, if we treat, then we can treat also with vanadium, with another chemicals that can be a substitute for iron. But in this case, we didn't observe any effect, even if vanadium has a chemistry which is quite similar to the one of iron. Now, we prepare these materials, and but how we can be sure that the organization of the fiber didn't change? So that what we observe is related only to the formation of these chemical bonds, these different chemical bonds, and not to a different organization of the fibers in this strip of chitin. You remember how we checked a few minutes ago? By X-ray diffraction. Mm-hmm. So if we perform again X-ray diffraction on this substrate, what we observe once more, these are the angular spread I was discussing you before, that the structure are almost in all the case with the same organization and with some additive that becomes even more organized than one it was in the starting material. Now, on
excuse me,
yes.
Can I ask a question?
Yes.
When you change the functional group of chitin,
mm-hmm.
I mean, you have a different steric hindrance. So how can you preserve the structure of the chitin? I mean, I guess that the structure of the chains of chitin are going to change if, for example, the functional group is much bigger or has different properties from the original one.
This is a very interesting question. I really thank you for the question. You have to consider that we are functionalizing nanofibers of chitin. So we are on the nanoscale, which means 100, at least 100 angstrom. One of these functional group is few angstroms. So there is no really sterical hindrance because the functional groups, the space occupied by this functional group is minimal compared to the size of the nanofibrils of chitin.
Yeah, okay.
Okay, but it's very
Yeah, thank you.
So then on this substrate, we did a mechanical test, and we did a mechanical test as I showed you before here. So stress strain, and we measure the properties, which is the maximum load, the maximum elongation, and the slope of this curve, which is called Young modulus. It is a measure of the elasticity of the material. I will not, in this case, I'm not going to show you this diagram, but I will show you only the final results. So what we can see, that when we functionalize the matrix, we got a slow decrease of the mechanical properties. You see here? Why this occurs? Because we are going to modify a substrate that's be already optimized as mechanical properties. So we are not surprised about this. But when we add iron, what you can see, that the Young modulus increase a factor of 10, so we drastically increase the Young modulus of the materials. But we lose to the maximum elongation of failure, was reduced about 1/4. If we do the covalent links, the Young modulus increase, the work to the first failure, so the amount of energy that we have to use to break the material increases a factor of 10, and also the maximum elongation increase. The first failure, work to the first failure increase a factor of 5, while the maximum elongation slightly decrease, 50%. But what is important to observe, that if we start from the starting material, if we do the chemical functionalization, adding iron or covalent bond, we have a positive trend in improving the mechanical properties. So we can, and the way back is that when we remove iron, by instance, you can see we have a decrease on the mechanical properties. So we have now a switchable system. In the present fire, we increase some mechanical property. If we remove iron, we decrease other mechanical properties. This and this is the last slide of my talk. I think it's already almost 5:25, so I'll stop here my presentation, and the rest of the time that we have, I will be more than happy to answer questions. Thank you.
Thank you. Can I ask another question? Sorry.
Please.
If I'm not mistaken, you used beta chitin because it's easier to modify.
That's right.
But isn't that convenient to use alpha chitin, even though it's more difficult to modify, but then in the end you have a more stable product, especially if you're trying to increase the mechanical properties of the material?
Your way to think is perfectly logic. But to do chemical reaction, you need something which is is reactive. And we try with all our effort to do chemical reaction on alpha chitin, but alpha chitin is incredibly stable.
Yeah, okay. I thought so. I'm not a chemist, so I didn't know, but I thought so.
Almost impossible to swell. It is almost impossible to solubilize in the almost all solvents.
Yeah, okay.
I will tell you that David tested 41 different chemical solvents, and no one was working properly.
Yeah, so it's very stable.
This is the number, okay?
Okay, yes.
Other question?
Yes. I don't know if it's a question for you. I would like to start from the sentence you write in this last slide about the potential of this waste in the bioeconomy. In Sardinia, we are currently promoting, for example, the oyster aquaculture, and this could certainly help in achieving the so-called critical mass necessary for reusing this waste that is also economical sustainable. On the other hand, we already have realities such as Nieditas, which therefore have a good production of mussels, although some of them are sold off the island. But the problem is that we have yet the solution for the reuse of bivalve shell. But the problem I personally encountered is that of being able to trace the entire waste supply chain. In fact, although there are companies that sell directly to the consumer, many others sell to the restaurant sector, making the traceability of shell waste more complex. So what we currently need maybe is the paths are defined for this waste that are able to recover it even in the phase subsequent to those of production. Do you think this gap can be bridged in the short term?
Yes, that was my question also at the beginning of the presentation. That can be an important gap to fill. How to recover all the materials from the restaurant, from the great distribution, because yes.
If you remember, I prepared one of the first slides that I showed. I try. Okay, this one.
Okay, sorry, I entered in the lesson late.
You can see this, I don't know, this is a slide in which, in this cartoon, basically I showed all the different way that I can see, but it is not ultimate for sure, how to manage with waste shell from mollusk aquaculture. Of course, there is a percentage of waste shell that are lost during the sorting or in the harvesting, and this cannot be, and are very difficult to recycle. Then after the harvesting, you can have different path. You can see, and the only one, in my view, that can successfully be used for recycling seashell is the one that goes to the companies that make cans or proceed seafood or vacuum dry, vacuum packed frozen without shell, of course, because the shell, in this case, all this shell can be easily collected. In the other case, when they are sold live to restaurant or are sold to restaurant after processing, in this case, it's much more difficult to collect the waste in shell. But I was showing this program that is now in Galveston in US, and this is one of the programs that are found on the web, but I'm sure there are many others, where there is an active group of people which is collecting shell, treating shell, and trying to put in back the shells in the ocean or in other place to rebuild substrate where oyster can grow again. So the collection is possible, but of course has to be based on the effort of the consumers and the users in the restaurants.
You know, it could be. That's a good idea. I tell you later.
Yeah, many people could be a form of social science. And
yes, I was thinking about a citizen science project. If you give an ecological perspective to people, yes.
But if you are able to valorize these materials, of course, they will be much more interesting. Think this, in the proximity of the sites of aquaculture, usually they use a lot of nutrients for fish. And the water surrounding these sites are highly polluted by nutrients. In this proximity, one strategy could be to grow up mussel shells. They filter huge amount of water. If I remember, 5 liters per day. Is correct, Stefano?
Yes, Silvia's more expert.
Anyway, you know better.
Liters, yes, liters per day.
So in this case, all the nutrients that are polluting, many phosphate or other material, other chemicals that are used for fish growth, can be used by the mussels, and then I don't know if the mussels are still commercializable, but if you give a value to the shell, of course, you are at the same time giving a use of a waste to a waste, and the waste is generated by a cleaning process to remove pollutants. It's clear?
Yes, thank you so much for your response. It was very interesting for me. I'm actually working in a Interreg project about circular economy in fishery and aquaculture. So,
where are you from, Elisa? Now, where are you?
I'm from Sardinia.
From where?
Yes, you working at the university there, or where?
No, I'm working at the International Marine Center, Oristano.
Ah, okay.
By the way, some
Let's
of
keep
the
in touch.
Yes, we've been contacted. Some of the oysters that I used, they came from Sardinia, and from a colleague, which is Piero Adis. I don't know if you know him.
Ah, Piero, sì, it was my professor at the university. Yes, it was also a stakeholder of our project.
Yeah, Piero is from the University of Cagliari.
Yes, and this topic is very interesting because here in Sardinia we have a lot of production of oyster and mussels, and particularly with my research center, we are beginning a new project for oyster aquaculture for Trasostrea gigas and Ostrea edulis. And so the reuse of this shell waste could be very important for our companies, because I work with small and medium enterprises, and this topic is very, very important for us, for our economy, and for our society. Thank you.
So please contact Professor Goffredo or myself, or better both us, and we can discuss about.
Yes, sure. Yes, let's keep in touch.
Contact me and Professor Goffredo, and we can discuss about.
Okay, thank you so much. I will do.
Okay.
Other questions?
I have a question.
Yes.
Are there any law restriction regarding the valorization of shell byproducts, chitin byproducts? I mean, I know that it is not easy to valorize fish waste byproducts, because if a waste from the if a waste is considered a feedstock, it cannot be valorized in another industrial area. So is it the same for this kind of byproducts, or there aren't any law restrictions?
There are law restrictions because they are considered a byproduct from food. So before you can use, you have to remove all the meat which is attached to the seashells. So there are, usually they remove or they make meat free of flea, they call it in English, but to remove the meat by thermal treatment or by oxidative treatment. But you cannot use the shell as it is. And this is why the reason in this program in Texas, they leave the shell for months under the sun, so the meat is degraded, it's not anymore, and then it can be used.
Okay, thanks.
Now, if you want, I can check what is the law, the number of the law, but this is not it's not central in this discussion.
Giulio knows.
Giulio knows for sure.
Yes. Okay, so if there are no other questions, I would suggest to close this section. Thank you, Giuseppe, very much for your lesson. Was super interesting. And of course, if you want to send me the slides, I then will provide the slide to the students. Actually, I have a question to the student. Are you receiving the email with the link for downloading the material?
Yes, we are.
Yes.
Yes.
Okay.
Yes.
Is it working? Yes, it's a WeTransfer stuff. So.
Yes. Yes.
Okay.
Yeah, absolutely.
Yes.
Okay, Stefano, I will send you, now I have to run away. I don't know if today or tomorrow, a PDF of the presentation, and then you can forward to the student.
Yes, thank you. Together with the registration.
Okay.
Okay.
What is written remain more in the time.
Okay. Okay. So thank you, Giuseppe. Thank you, everyone. We'll see. We have the next meeting tomorrow morning at 9 o'clock. It will be in Italian tomorrow, the presentation.
Thank you.
Thank you.
Thank you.
Okay.
Thank you. Bye.
Thank you.
Bye-bye.
Bye.
Thank you. Bye.
Bye.
Goodbye.
Bye.
Goodbye.
Bye, everybody. Ho fatto l'eco.